So we have the last presentation before a panel discussion. And so let's welcome onto stage Roberto Saltini, lead consensus protocol researcher at PegaSys. And he'll be talking about IBFT 2.0, a robust PoA BFT consensus protocol for Ethereum. Thank you. That's a mouthful. There you go.
Hello. Today I will be speaking about IBFT 2.0. Well, actually, my objective is a bit more ambitious, just speaking about this protocol. What I want to do, I want to use this protocol as a case study to outline how to actually design a robust consensus protocol. But before diving into it, let's take a step back and let's look at what IBFT is. So IBFT is an Ethereum consensus, blockchain consensus protocol, which falls into the category of the proof of authority consensus protocol. So only a subset of the nodes called validators are allowed to produce blocks and to create blocks. It has a dynamic validator set. So basically, the set of validators can modify over time. Validators can vote other validators in, other nodes in to become validators, or they can vote validators out. It is Byzantine fault tolerant, which means that it can cope with up to 1/3 of the nodes being malicious. And finally, it provides immediate finality, which means that basically any block that is added to the blockchain is final, and in other words, there are no forks. So why is IBFT actually useful? Well, we saw the talk before that was speaking about Click and Dora, and this type of proof of authority consensus protocol don't provide a Byzantine fault tolerance. So actually, IBFT enriches this family with a consensus protocol that has this Byzantine fault tolerance property. It is well suited for small and medium-sized networks where not all of the nodes necessarily trust each other. You can think of applying this to side chains or private side chains that are then pegged to the main chain, and finally allows for a dynamic network. As I said before, the set of validators can change over time. So as the network grows, the more validators, the more nodes you add, the more organization enter into the network, the more validators you can add. So now we are actually ready to explain how IBFT works. Essentially, IBFT can be considered as running successive instances of the IBFT block finalization protocol. And the aim of each of these instances is to create a block, which is implicitly final. So you can see on, you can see on the left-hand side the general H instance of the IBFT block finalization protocol. The aim of that instance is to create a block for height H. So through a series of message exchanges, the block is eventually created. As soon as one validator or more than one validator create the block gets propagated to the other validators. And at the same time, another instance of the IBFT block finalization protocol is started, at this time for the next height, so height H+1. And again, through another series of message exchanges, the block with height H+1 is created. And the protocol proceeds in this way, and always adding blocks to the blockchain. But now let's look at how each of these instances looks like. It's essentially a PBFT protocol plus block locking, which is organized into rounds. The aim of each round is to create the block. And if the block cannot be created in that round, then a new round is started, and in this new round, it is attempted to create the block. The length, each round has a prefixed length. The length is exponential to round number. So in this case, we have the standard 3 phases of PBFT. We have a block proposer. In this case, is validator 1, which proposes a block by sending a pre-prepared message, which includes the block. All other validators reply with a prepare message. If validators receive enough pre-prepare and prepare messages. They will lock on the block included in these messages. And if they lock, they will only send messages for these blocks. This is done because the objective of this is that if a block is created in any round, the protocol wants to be sure that the only block can never be created in successive rounds. The next phase is the commit phase. As you can see here, the commit messages are delivered after the expiry of the round timer. So we go through a round change phase, where at the end of this round change phase, the block proposer is now validator 2. Again, we go through the same 3 phases, and at this time, the block is actually created. And so, after this, you'll have the next instance of the IBFT block finalization protocol. So, strong of our definition, we can proceed and look at the journey from IBFT to IBFT 2.0. So there are a few steps. The first step is what you need to do whenever you come across a consensus protocol that you want to implement. You need to look if there is a mathematical analysis of this consensus protocol. If there isn't, well, you need to do one. And if you find issues, well, you need to find a solution to this issue, and then you need to mathematically analyze your solution. Not only, if you really want to be sure that what you're specifying is correct, you need to build a formal specification and run a formal analysis of the protocol. But this actually will only allow you to show and to be sure that the protocol is robust. That's not enough. You also want a performance protocol. So then you have a performance improvement phase, and then you repeat the steps. So from step number 3, again, you do the mathematical analysis, the formal specification, basically until you're satisfied that your protocol is performant enough. Let's start from the first point, which is actually has 4 main sub-steps. So to do a mathematical analysis, you need a mathematical definition of the protocol. Then you need to define the system model. So you define which is the system in which you want to deploy your protocol. You define what robustness means, and finally, only finally, you can actually perform the analysis. So let's look at so in the case of IBFT, there was no mathematical definition of the protocol, so we did create one. And then we define the system model. When you define the system model, typically you want to define 3 submodels, the network model, the failure model, and you want to define the properties of the cryptographic primitives that you are going to use. Let's look at the network model. The network model essentially describes which is the maximum message latency on the network. And in literature, you generally have 3 main network models that are considered. You have the synchronous, where you know the maximum message delay, you know the value. Messages won't take more than that time to be delivered. You have the synchronous one, where basically the message delay is unbounded, can be any value, the value is unknown. And in this condition, there is a proof that shows that no consensus protocol is guaranteed to terminate deterministically. And then you have the partially synchronous network model, which can be divided in 2 submodels, the eventual delivery, where basically you know the messages will be delivered. There is a bound of the message on the latency, but this bound is unknown. However, it's constant. And then you have eventually synchronous network model, basically where you assume that there is a point in time called GST, or global stabilization time. Before this point in time, the network is asynchronous, so you can lose messages. But after GST, the network acts synchronously. And the model that we considered is this last one, because it's the model that has the weakest assumption, and at the same time guarantees deterministically termination of the consensus protocol. Then you need to define the failure mode. Typically, there are 2 failure modes that are considered. One is the fail-stop failure mode, where nodes that fails just stop sending messages. And there is the Byzantine one, where nodes can act maliciously. Again, we chose this one because it's the model that has the weakest assumption, or you can also say that it's the one that is the strongest failure model. That's because you wanted to ensure that IBFT is actually a protocol that performs in the wider possible number of cases, and it's actually a general protocol. So we didn't want to constrain the system to specific behavior. We wanted to allow the model to describe the widest possible number of environment conditions. And lastly, you need to define the properties of the cryptographic primitives that you are planning to use. Typically, you choose a collision-resistant hash function. You have a signature scheme, which usually provides uniqueness and unforgeability. Before actually doing the analysis, there is something more you need to do, which is to define what you mean by robustness. In this case, we relied on a definition provided by Garay et al., which was provided when they did the analysis of the Bitcoin blockchain protocol. And robustness, in this case, can be thought as a conjunction of two different properties. One is persistence. Persistence essentially says that if a validator creates a block at 8 heights, another validator creates another block at 8 heights, these two blocks must be the same. Not only, there is another condition which says that if a validator adds a block to its own local blockchain, then that block will eventually be added to the local blockchain of any other validators and nodes. And then you have liveness, which says that if a transaction is sent to all validators, well, that transaction will eventually be added to the local blockchain. So strong of our system model and robustness definition, we can proceed to analysis. So we did, and we discovered two interesting results. The first one is that there is no optimal Byzantine fault tolerance. The protocol doesn't guarantee optimal Byzantine fault tolerance, especially for a network of size different from 3f+1, so different from 4, 7, 10, 13. The Byzantine fault tolerance is not optimal, and determination is not guaranteed, even if you consider that only one validator might stop. Let's look in more detail into these results. So the first one, I give you an example. You have a network of 5 nodes, of 5 validators. The optimal Byzantine fault tolerance in this case is 1, but we'll see that the IBFT doesn't provide any Byzantine fault tolerance in this case. So IBFT, for a network of 5 validators, says that basically it's enough for 3 validators to exchange messages to have a block finalized. So what can happen is that the proposer is malicious, can basically clone itself, and it can cooperate with 2 nodes to create block B1 and with other 2 nodes to create block B2. So you end up with 2 honest nodes creating block B1 and the other 2 honest nodes to create block B2 for the same height. So in this way, the persistence property is violated. Let's look at the termination problem. The termination problem is basically due to the locking mechanism. So because of network latency, some messages might not be delivered within a round time, within the round number 0. And so one of the proposer, like V1, might lock on block B1, and then you have a round change. At this point, the new proposer, which is V2, is not locked, so can propose whatever block it likes. It might propose block, let's say, B2, which is different from B1. And then at this stage, at this point, the network is all synchronous, so all three will lock on the same block. And then eventually, one validator stops. And basically, you are left with the maximum of 2 validators to be locked on the same block. And considering that you need a minimum of 3 validators to agree on the same block to produce new blocks, you end up in a sort of deadlock situation. So we found 2 issues, and now we need to identify a solution. So for each of the issues identified, basically, what you need to do, you need to identify the missing core properties. If you see that there is more than one solution, well, you need to evaluate the pros and cons of each solution and then actually select one. So let's look at the persistence issue. What we identified is that, let's say the Q is the minimum number of validators that are required to collaborate in order to create a block. If you can guarantee that any 2 set of Q validator always intersect in honest validator, then persistence can be guaranteed. So this led basically to modifying the formula for calculating Q from the old one to the new one, which is basically a scaling of 2/3 of the nodes. Just to give you an idea, basically this formula says that there is no change for a certain number of validators set, but there is actually for some numbers like 5, 6, 8, 9, the number of validators is increased by, the minimum number of validators is increased by 1. And this solves the persistence issue, but we are still left with solving the liveness issue. So as I said before, the liveness issue or termination is caused by the block locking. So essentially you have two solutions at hand. One is to allow relocking, so you can allow relock on a different block, and this will prevent the deadlock that we saw before, but you need to be careful. You need to allow the relocking only if you can be sure that the old block had never been created before. Otherwise, you can end up in violating the persistence property that we defined before. And the other solution is actually to remove the block locking. But then you need to add more information to the messages to be sure that if a block is created in one round, that's the only block that can be proposed in any successive round. So we found the first solution is kind of more based on, it's in alignment with Tendermint. The second solution is more in alignment with PBFT. So we have two solutions, and now we need to evaluate the pros and cons of the two. So the pros of the first solution is that when there is a round change phase, the size of the messages is smaller. The pros of the second solution is that it's actually possible to reduce the minimum number of phases from 3 down to 2, which actually means that you can improve the block latencies by 1/3. And the second solution also ensures a quicker recovery from a bad situation where you have a malicious validator or the network is unstable. So in this case, we have two solutions. We need to select one. We decided to select the second one. And that's because our specific use case is to consider networks where typically, where small, medium-sized network, where typically nodes trust each other. The network is synchronous. And while we want to be robust to a malicious node or a synchronous network, we want to optimize for the standard condition, which is all validators honest and the network is synchronous. So I just want to outline the preferred solution. We remove the block locking and we add the pre-prepare and prepare messages to the round change message. And we also add the round change message to the pre-prepare message of rounds higher than 1. And basically, in this way, we can achieve both termination and persistence. The next step on our journey is the mathematical analysis. We did that. The paper is not published yet. The steps after this one is a formal specification and formal analysis of the preferred solution. We started our work using TLA+. It's still a work in progress, so there is still work to be done on this front. And this basically leads us to IBFT 2.0, as it is currently implemented in Pantheon. But as I said before, robustness is not everything. We also need to care about performance. And this is where what I call IBFT 2.x comes into play. There are two important improvements. The first one is, I mentioned that before, is reducing the minimum number of phases from 3 down to 2. This is what I call very low block latency. And the other one is about reducing the message size. Let's look at the first one. So the first solution is based on the paper best case complexities of a synchronous consensus from Jute et al. And in the condition where all validators are honest and the network is synchronous, you can actually create a block after only 2 phases. And this is a pretty standard condition for our use case. Otherwise, if this condition is not met, then the protocol degrades gracefully to the previous condition, so I mean to the 3-phase condition. So graphically, this is IBFT 2.0, and this is what the improvement allows to basically decrease the network latency, the block latency by 1/3. I think this is a very important improvement that cannot be, for example, applied if you had chosen the Tendermint-like solution. The other problem is the message size, which is the problem where, as we said before, the round change message requires to have a number of pre-prepare and prepare messages equal to 2/3 of the number of the total validators. So in a network of 4 validators, you have 3 between pre-prepare and prepare messages added to the round change messages. And you have 3 round change messages added to the pre-prepare message for round 1. How we can solve this? Well, we can take advantage of the property of the gossip network, where if a message once a message is received, is immediately gossiped to all of the other peers, which means that if a message is received, well, then it's immediately transmitted and broadcasted to everybody else. And this basically is something that Tendermint relies on. So by bringing this in, we actually bring some of the pros of Tendermint that we lost when we chose our PBFT-like solution, and you can actually achieve the best of both worlds. So in our example, whenever round change message is received, it's actually immediately transmitted, broadcasted to everybody else. So we don't need to add the round change messages anymore in the pre-prepared message. We can just add the hashes. The hashes are important because we need to identify which of the 4 round change messages that we might have received. We need only to select 3. We need to identify which of these 3 messages we are selecting. The second improvement is basically having aggregated signatures in the round change messages to reduce the size of the round change messages. And with this one, we basically completed our journey. Well, actually, not really. We should go back to the 3rd stage, but while we leave it for today, I will actually go in more details on this on the workshop in SW on Monday on protocols and formal methods. I will have a more in-depth presentation on the same topic. Just a few links: IBFT 2.0 in Python, the Twitter handle for PegaSys, myself, the IP650 where IBFT was originally described, the correctness analysis, our correctness analysis paper, where we describe the issues that I presented here, and we sketch a solution, and then acknowledgments to the EDCON organizers, PegaSys, and Jake for helping with the diagrams. Thank you.
Well, so what are the next things for your research and sort of what's in your purview?
So the next step for us is basically to go through the formal verification process of the protocol, and then to integrate the improvements that I've outlined, and eventually to actually standardize the protocol, so collaborating with other partners, with other clients in the ecosystem to ensure that the protocol is implemented by other clients so that we can achieve interoperability, and we can build we can basically rely on multiple clients being deployed on this type of network. That's basically the next step.
Great, thank you.